Last video we already know how to apply the extended Kalman filter to show the nonlinear motion. So today we continue to talk about the last part of the Kalman filter topic. That's unscented Kalman filter. This is the hardest one in the three type Kalman filter: standard Kalman filter, and is unscented Kalman filter. This one is really a typical map inside. So we already know the standard Kalman filter lesson. We use the constant velocity to build up the model, right? So a constant velocity model is one of the most basic motion model we use to object tracking. So, but there's many motion model. For example, constant turning rate and velocity magnitude model, we will call the CT or V. This model we will go deep detail later. So, and another thing is constant rate and acceleration, or constant steering angle and velocity, or constant curvature acceleration. So, let's thinking if the car go constant velocity, so what do you think what happened? What do you think they go to the curvature curve or go to the turning point, and what the estimation is correctly with the standard Kalman filter, with the constant velocity, do you think is correctly the estimation when the car turning? Another question, what do you think? As some vehicle goes straight right here, and then go into the turn. If we apply a Kalman filter to track the vehicle, what do you expect happen with our estimation result for vehicle position? What do you think? So the position estimations would tend to result outside of actually driving cycle. So the estimation right now incorrectly, right? It's not correct anymore. And you're just thinking, we always in the previous example, we always assume they go to straightforward from point A to point P, constant velocity, right? So right now we build up the model to have they get the correct estimation when they go into the turn. Not only that, they not only go to straight. Right now we build up the model. They have to estimate the car go to the turning, right? So the first time we had to build up the process model. Look like another example we looked last video. We start the first step we had to build up the process model, right? So right here we have the state variable for this model, ps py. It's the same last extended Kalman filter last video, okay? But right now we don't use vs with vy anymore. Right now we create the state variable v, velocity, and psi is your angle, and psi dot it means your angle rate, the turning rate, and your angle right here you see. And right now we had to know the state variable your dot. I mean psi dot right here, the train number turning rate. So right now we have 1, 2, 3, 4, 5D, right? So this is the time k and time k plus 1. So what the process model app help you estimate the state of time k plus 1. That's the problem we need to show right now to figure out what the process model. You have the yaw angle right here, the turning rate, and you have the v, this velocity. So in this model we say, remember we assume the constant velocity and constant magnitude velocity and constant turning rate, right? We will call this CT or V. So I give you example. In three state vector right here, what do you think? With the state vector general, we have the position, PSPY, velocity, and yaw angle and yaw angle rate. So one of the three vector state vector right here, which one the car goes straight? Let's thinking. Look at right here. The yaw angle rate right here is zero. It's different the other two right here, right? It means they go straight. The yaw angle they don't change. It's equal zero. It means the car will go straight right here. So step back to two. The question right here, which one above is present or driving straight path in number two, right? Because the yaw rate is equal zero. Okay, after we already have the state vector position PSPY V your angle and your angle rate side dot right here to see how to train up the rays, the yaw angle rate, right? So my question right here, how to build up the process model to estimate the state vector up at the time k plus 1. As you know, the process model they had to, if you know the state vector of the time k and the noise process, the process noise at the time k, we predict the state vector at that time k plus 1, right? That's our process model. So we use the difficult right here to see how to change the state variable, right? So we call the S dot is element dot inside PS dot, PY dot, V dot, side dot, and side dot dot. So right now, how we find the chain of the state variable right here for each element right here depend on the state variable element right here. For example, we got the PS dot right here. You look at the picture, you can see PS dot equal VS right here. V, they have two components, VS and VY, right? So PS dot, it means the transfer position equal the velocity is that direction, right? So PS dot, we look at the right triangle right here, you can easily see it's a cosine sine times V is the VS, and similar way what the PY dot right here, you can look at the right triangle right here, you can get the PY dot right here side, right? And similar way, let's thinking how about the V dot, side dot and side dot dot. Remember we assume this model is constant magnitude velocity and constant turning rate. Remember that. So question right here, we already have the PS dot is cosine sine times V, right? So what the PY, you can guess one of them, right? It's a sine, right? And how about another element into the transfer of the state, V dot, side dot, and side dot dot. Let's continue with another question right here. What the transfer rate of the velocity? What do you think? It had to be zero. Why? Because we assume it's the constant velocity, right? And another thing, how about the turning rate? Turning rate don't change, right? Turning rate. So we keep the same. B. Okay, how about the turning rate? Acceleration of the turning rate. Acceleration is your angle. It means your angle side dot dot right here. What do you think? It's zero because we assume the turning rate is constant. So acceleration of the yaw angle right here has to be zero. Easy. So we find the differential equation. That's the chain of the state variable right here, right? PS, PY, and V dot, side dot, and side dot dot, right? It's easy to get this value. So at the time we had delta t, the the trends from time tk plus 1 minus time tk, right? And we got the integral, right? We got the integral to get the state variable at time k plus 1 equal time k plus the integral the time tk to tk plus 1, all the differential equation you already got last time. So right now our job is figure out what the integral for each element right here. So the easiest one is mean to find the last three row right here. V dot, side dot, and side dot dot. So how we find that? For example, we integral from the time tk to tk plus 1 v dot. First time we had to figure out what is this in three row right here. So v dot t dt. What do you think? Let's think a little bit. Is equal 0. Why? Why is equal 0? Because we have some the constant velocity magnitude, right? So this one equals 0. So it's the second thing, side dot dt. Side dot dt right here. The integral right here. How much? How much? What do you think? It's means side dot k times delta t, right? You get easy because it's a constant turning rate. So we get outside and you inside delta t, you solve the integral, right? And the last item is about the turning acceleration of the yaw angle. Side dot dot right here. What do you get right here? The last column, the last row. You're just thinking we assume the turning rate is constant, so rate had to be 0, right? So we will guess the three last row right here, the answer. But what happened the first two row, and how do we get the integral there? Now let's try to find the integral, this one, from time tk to tk plus 1 vt sine dt. And to solve this integral, we already know the constant velocity we put gets outside, and we solve this integral. It's really hard, right? But anyway, I think it's if we can do that, or you can go to the this link, the website. You can see how they solve this integral to get a result for two column right here. And here's is the question right here. So which one? So that's integral. For the first one, what do you think? You can get your intuition about the integral. You look right here, the cosine side. You can think in a b. But you want to detail how to show. You go to the link of the website. You can see how they solving that. Okay. And this is a B, right? Or here's a B, right? And the first row and the second row, you can see it's A right here, right? So in generally, we have the solution of the integral. Give us the state, estimate the state variable. You have the function of the process to estimate the state variable time tk and tk plus 1, right? Right here, the solution. But you look at it when the turning rate equals 0, is what do you think? It has to go straight, right? It had to go straight. It had to go straight, right? And right now, what the position? The trend position in the x and y, how much? This is the question right here. You can calculate the trend as position over time when the turning rate equals 0. It's easy, right? You can look at the right triangle right here. You can see it. When the your angle is equal to 0, and you got the chain of S, it means V times cosine and delta t, right? And similar way for the when the angle right here is equal to 0, so we also got the position, the chain of the position in the Y, right? In the Y, right? It means right here is E equals V sine delta t, right? I think you can go with me so far, okay? Let's look at the right triangle right here. You can get easily answer. So that's a special case for our process model. So continue. When we build up the process model, we talk about the noise, right? Process noise, mu k right here. So what do you think? What impact the system, the model in the model right here? They had to tie up the element impact to the model right here. This means the acceleration, longitudinal, and acceleration, longitude acceleration, and the acceleration of your angle, right? Side dot dot. They will impact to the model, right? So and right here the longitude acceleration noise, and we have your acceleration noise. They are the not that's the distribution. You have mean 0 and the sigma square a for a and your dot dot right here. So come back to the model, we had to plus with the noise. Look like another way we do. Last video we always plus the process noise right here, right? So let's go. For example, how we find EDCAB right here. It means we know how the longitudinal and the acceleration right here, acceleration angle right here, impact for each one right here. How this one impact for each element here. So we have the E, D, E, C, B, A, right? So what the E is how the to this one impact to the E right here, impact to the angle rate, your rate right here. This means that delta t after the delta t we have the you multiply for the noise of the impact of the yaw right here. How about the d? How the d impact to the yaw angle? That's a question I saw right here. What the influence of the mu a and mu acceleration and mu the acceleration of yaw rate on the velocity? On the velocity, how this one impact on the velocity, how this one impact to your angle, and how this one impact to the your rate. That's we had to figure out, right? And that's question right here. I mean, for the velocity, we have this one, the impact, the noise only impact from the acceleration. So we got delta t times mu a v a and mu a k, right? How about the what influence of the a and your acceleration your angle on the your angle? How about that is 1/2, right? Uh, 1/2 delta t square. I think you know this one is quite similar last extended commuter. And what influence of mu ak and mu your dot dot on the your rate is delta t time mu your rate dot dot k, right? That's the impact for each one on the state variable vector right here for the noise. So we already find last three row right here. So how A and B. So acceleration your angle impact onto the position. How to know that? We assume the thinking the your rate right here if the increasing, right? If the UR acceleration increasing, maybe the position is go here is positive, or maybe it's go to decreasing is negative. The position of the cars right here. But in the system, we assume the trend of acceleration rate. Acceleration of your angle very small, so we can skip this influence from the acceleration of the your angle. So we just care about how the acceleration, longitude acceleration impact to the position PS and PY. And to do that, we had to know, we had to calculate the integral, but we have the simple way approximation method. We're thinking the impact of acceleration, longitude acceleration impact this position and this position is the same. It is correct if the turning rate is really small. Okay, and to do that, we saw the we had the answer right here. What would the acceleration offset be if the car driving perfectly straight? Because we assume they go to straight, this is the fast way to guess the noise, the acceleration noise impact onto the car, right? On the position of the car. And regards for the S acceleration offset right here, A, right? And similarly, regards the for the B, for the acceleration offset in a Y, it means B right here, 1 over half delta T square sine, okay, mu AK. That's the impact of the mu A, linear longitude acceleration. Right now we skip the your angle as acceleration of your angle, right? Because the trend of the acceleration your angle really small, so we skip that one. So in generally, we already built up the process model right here, and this one is impact process noise right here, right? And it's really good, right? For continue next step, but we are thinking about in extending Kalman filter, we use the Jacobian metric to linearize nonlinear function, right? And what do you think this function right here is a linear function or nonlinear function? Of course, nonlinear, right? And in the unscented Kalman filter, on the other hand, we don't need to really linearize nonlinear functions. Instead, the unscented Kalman filter will use the unscented transformation methods. Okay, we will take the representative point from the Gaussian distribution. This point will plug into the nonlinear equation. I will talk next how we apply the unscented transformation to solve this problem. Okay. For example, we remember this Gaussian, right? This ellipse represents for the Gaussian with the mean S and covariant P right here at time t equal tk, right? So in time tk plus 1 and how they prediction the state variable from time t equal k to tk plus 1, how they get the same Gaussian distribution right here is it's a time tk plus 1 and covariant k plus 1 right here. And you know, in the Kalman filter, after we already update measurement, we have the posterior belief, okay, and we estimate we prediction the state for tk plus 1, right? I think you remember that. And the problem right here, if we have the standard Gaussian, we have the Gaussian right here, Gaussian distribution right here with the S and P, state variable and covariant right here. So our problem we have the linear, if we have the linear function right here, and we can apply the standard Kalman filter with the S and Q right here. Q is a covariant matrix of the process noise, and optimum is E if each one is a linear right function. We can apply for the Kalman filter to show the estimation state variable at time tk plus 1 right here easily, right? If I say if the linear function, but our problem right here, we already saw our model right here is not linear, right? It's a non-linear. So problem right here, we have the f function f right here is non-linear function. So how we have the Gaussian distribution in time tk plus 1 and apply Kalman filter right here? That's the question. We can use the I think the approximate numerical approximation technique to show this problem. And even if we got the distribution right here, it's not really non-Gaussian, right? But the unscented transformation help us to continue until we get the Gaussian distribution right here. Right here, you see right here, we want to get the time k plus 1. It had the Gaussian distribution right here, right? And with the S and P close to the S and P right here. So the methods we apply right here, we call the unscented transformation, right? We don't use the linearized and function anymore. We apply the unscented transformation right here to get the Gaussian distribution answer right here. And how to do that? The unscented transformation use the sigma point. I will talk into the next video. Okay. I hope summarily in this video we already how to derive the process model here, and instead we get the answer, the model right here, how we get each element into the model. And this model we call the CTOV. It means constant turning rate and velocity magnitude model right here. We assume the two values. Remember the constant turning rate and the constant magnitude velocity for this model. It's help us to show when the car go into the turn. I can estimate correctly when the car go to the turning point, right? Okay, that's all. I hope you understand how we got the process model. Okay, next video we continue how understand what the unscented Kalman filter right here. We apply the unscented transformation to solve this problem. Okay.